Okay. Now we want to do it with a better way. So we're going to be saying, you know what? Here is your buffer. Okay. From 0, let's say from 0 to 9, which means it's 10 locations. The problem is much easier than this. Get a counter that is initially 0. Whenever the producer produces, the counter goes +1. And whenever the consumer consumes, the counter goes -1. So what does it mean? Let's say that the counter is now 5. So you have 5 produced elements in there. When the producer produces again, now the 5 is going to be 6. Then the consumer consumes 2. So the counter is going to be 4. Why is this? Because now what's in the jar, what's in the container is 4 elements to be consumed. So that made the problem much easier. You think so, right? Let's see. Here is the while true, the external loop. Okay, infinite loop. And then you say, look at that. While counter, this is the producer, eh? This is the producer. So while counter equal buffer size. So if the counter is 10, what happens? You tell me it can never be 10, it's going to be 9. No, the number is 10, right? From the index from 0 to 9, but the number is 10. So if the counter is 10, the buffer size, whatever that is, it means it's full, right? The buffer is full. So there is no place to produce. So here we say, do nothing. Remain where you are. Keep looping here until one place is empty. Okay. So you're going to only exit this loop when the counter is no longer the buffer size. When the counter is 9 or less, you will exit. So you have now a location to produce in. Here it is in. Okay, you produce the next product or produced, and then you increase the in by 1 and increase the counter by 1. Why? Because you have produced 1 extra element. So the counter will increase by 1. This is the producer. How about the consumer? Look, here the consumer. While counter equal 0, do nothing. This is helping you to prevent underflow. Because, if you produce when the counter is 0, you are going for underflow. And this, in the producer code, is helping you avoid overflow. Right? Because if you produce while the buffer is full, you are going for overflow. Now, here is the next consumed, and then you add the out equal out plus 1, just like the last time. But here, you say counter equal, counter minus 1. You reduce the counter by 1. Okay, counter minus or counter equal counter minus 1. You decrease the counter by 1. Here, you increased the counter by 1 because you're producing. Here, you are consuming. And problem solved. You think so, right? Look at the problem here. And this is a reader-writer problem, by the way. Look at that. We have something called race condition. What is it? Before we see this, look at that. What is counter plus plus? If we go for a kind of assembly like, you're going to be loading, okay, R1, register 1, and counter. So the value of the counter went to R1. Then add R1, comma R1, comma 1. Or increase, it depends on. So you add it and then store R1 and counter. So if the counter here is 5 as an example, R1 will be 5 because you did the load here. Then add R1, comma R1, comma 1. So the 5 is going to be 6. You added 1 to 5. So here R1 is 5. Right? 6, sorry. And then you store R1 to counter. So now this became 6. Same way with minus minus. So you're going to be, the minus minus here is going to work like this. Load R2 counter, subtract R2 and 1, and then store R2 and counter. Look what's going to happen. Here is the same counter. It was 5, right? Load to R2. So here is R2. So R2 is 5. Then subtract 1. So now R2 is 4. And then store. So now counter is 4. Why am I saying this? Look, counter plus plus is not atomic. What does it mean to be atomic? It doesn't execute as one unit. It's actually 3 statements. Look, it's 3 statements in the lower level. The load, add, and store. Or, in higher level format, you get the value of the counter, put it in register 1. You increase register 1 by 1, and then put the value of register 1 back to counter. If you're decreasing the value of counter, so minus minus, same way, get the counter to register 2, and then decrease the register 2 by 1, and then take register 2 and put it to counter. The problem here is as follows. Look, here, let's say you have process 1 and process 2. Process 1 does counter plus plus, and process 2 counter minus minus. Counter initially equals 5. Okay? Look at that. For our bad luck, P1 and P2 are synchronized. So process 1 and process 2 are synchronized. So and they are in the same step and working in parallel or concurrent. So step 1 here, register 1 equals counter. But in the exact same moment, here register 2 equals counter. So here, register 2 is 5 and register 1 is also 5. Here, register 1 equal register 1 plus 1. Register 2 equal register 2 plus 1. Minus 1. So here, register 2 became 4, while register 1 became 6. Then you say here counter equal R1, and here counter equal R2. See, the PC, the program counter, is moving so that here is the PC, here is the other PC for the other process, so that, they come here together. So what is the value of counter? Well, if this one executes last, then the value is going to be 6. If this one executes last, then it's going to be 4. And neither 6 or 4 is right. The answer is 5. Why? It was 5. You increased by 1. You decreased by 1. So it should remain 5. But no, it will be either 4 or 6, and both of them are wrong. Okay, so this is what's happening here. So as an example here, you are reading the value of R1. You increase the R1, and before you do the store, R2 read. And then you increase the R2. Here, counter equal, register 1. So here counter is 6. Okay, but then counter equal, register 2. Now counter is 4. And 6 is wrong, 4 is wrong, because both of them, that's increasing and then decreasing. It should actually be 5. Okay, what is the problem here? It's not atomic. And that's what we call the race condition. And this is going to be solved in chapter 6. Okay.